So concept of resistance. So we have seen Q equals minus Ka. We have seen Ka delta T by L. Okay, this is a simple formula for heat conduction equation. But this can be similar to your electrical conductivity also. So electrical analogy, if you say I equals E by R. Okay, E is your potential difference or voltage difference. Potential difference. Okay, I is your current. Okay, electrical current. R is resistance. Okay, now 1 by R is called constant of proportionality. Constant of proportionality. Proportionality. Okay, now how it will look like when we draw electrical circuit? We draw resistance like this. R 0.1 to 0.2. Okay, and we are applying potential difference E and current moving I. So E equals IR, right? Now Q minus Ka T2 minus T1 X. Okay, I have one slab T1, T2. Okay, T1 minus T2 is actually my potential difference. Okay, E, I can write T1 minus T2. Okay, this is potential difference actually. You can say equivalence if I make. Okay, and slab thickness X. Okay, now X by K, T2 by X equals T2 minus T1, T1 minus T2, because minus sign absorbing, X by K A. So I can write T1 minus T2 by R. R can be equal to X by K A. Okay, so this is called thermal resistance. So I can say X by Ka thermal resistance. Okay. Now if I have two slabs, instead of one slab I took two slabs or two metal, iron and copper maybe. Okay, two metal. So I'm say here actually engineering drawing simple. When two metals we are drawing, so we'll be putting different hatching. Otherwise, it will be looking like same metal. Okay, different hashing line. Okay. T1 temperature here, T1 temperature and T2 temperature here. So it will go like this. Temperature may be different conductivity or different thickness. Okay, this is resistance R1 as per electrical analogy. R2, this is X1, X2, and heat transfer is happening Q. Okay, if Q is input, same heat must be output because energy must be conserved, right? So in electrical energy, how can I write? T1, T intermediate maybe, and T2. Okay, T intermediate. So R1 plus R2 are electrical analogy. So here in my heat transfer system, I can write like this: X1 by K1. This is maybe K1. This heat conductivity. This is K2 heat conductivity. A plus X2 by Ka 2A. Okay, and Q equals T1 minus T2 by R. Okay, very simple. Two slab, we are assuming same area. If area is different, then A also will be different. But this is called electrical analogy. So if I have many metals, like say iron, steel, copper, and many metal in series you have connected. Especially this formula is useful where you have insulator. You have metal pipe. You have one insulator. How to calculate heat? So you know internal heat, you know external heat, and you are resisting heat transfer. So internal how much heat is there, you do not need to know. You need to know your K value, this one, K value this one, area this one, area this one. Based on that you can calculate actually heat flow rate. Okay, resistance in parallel. In series you have seen heat transfer rate, like electrical analogy you have seen, R1, R2, R1, R2. So R becomes R1 plus R2. So similarly, if I have two metal in series, like one is here, another is here, okay, and heat is coming, Q heat, same heat will be going out, okay, and R1 resistance is here, R2 resistance is here, temperature T1, temperature T2, and this distance is x. So formula becomes R1 by R1 plus 1 by R2. Okay, so R1 equals x by K1A1, R2 equals x K2A2. And if I have another slab also, I can write like this. Okay, so if I have three slabs, so in that case I can write like this: R3 equals x by K3 A3. Okay, okay, so I have to make difference in hatching line also, okay, because three different metal I am assuming. So in that case my formula will be modified as 1 by R equals 1 by R1 for two metals, for three metals. Okay, 1 plus R2, 1 by R3. Okay.